Hello everyone and welcome to Network Playroom. This is the 6th video in the Christmas calendar series, and today we're going to talk about route summarization. Yesterday we went over different ways to generate a default route, and I mentioned that the default route is the ultimate summary route. But of course it's not the only summary route, and in this video we're going to look at how smaller specific networks can be represented in one quote-unquote super route. I'll describe the process at binary level, so some familiarity with binary conversions is required or recommended. And there are other ways to find the summary route, but it's good to know the fundamentals. But before we get started, let's have a quick review why summary routes are needed. So in large networks, hundreds or even thousands of network addresses can exist, and it is often problematic for routers to maintain this volume of routes in their routing tables. So route summarization can reduce the number of routes that a router must maintain because it is a method of representing a series of network numbers in a single summary address. So let's look at the scenario on the screen here. So R2 and R5 have a bunch of /24 networks connected to them. I've chosen random ranges for the network so the summary routes are not obvious, and we'll actually have to think about them a little bit to produce an optimal summary route. When I say an optimal summary route, I mean the most specific route that covers all these networks as accurately as possible, but not more. So we could use a 10.42.0.0/16 or even 10.0.0.0/8 summary route, and it would be valid, but it would also cover other networks beyond the range. So you could use 10.42.0.0/16 or even 10.0.0.0/8. But again, these would cover more than the addresses in this range. And similarly, we could use 192.168.0.0/16 on R5. Again, like this. But this would cover too many networks, way beyond this range. That's not what we want. What we want is to find the most accurate summary route. Now, I don't want to spend too much time on decimal to binary conversions and vice versa, but I'll quickly demonstrate how I like to convert the numbers. I like to play a bit positions game. So we're using 8-bit numbers, so there are 8-bit positions, and they are 128, 64, 32, 16, 8, 4, 2, and 1. Now, I try to figure out which of those numbers I need to use to add up to and equal to the number I want to convert. So those numbers will be marked with a 1 in their respective bit positions, and the numbers that are not used are marked with a 0, and the result is the binary number. So let's take 200, for example. So what I'm going to do is that I start with the highest number that fits within that value, and that would be 128. And now I mark it as 1 in the bit position since I've used it. So I put a 1 here. And then I subtract 128 from 200, so now I'm left with 72. And I repeat the same process, and the highest number I can fit in 72 is 64. And then I'm left with 8. So finally I mark 8 with a 1 and the rest that I didn't use with a 0. So like this. 0, 0, 0. And that is the binary number. Now, let's do the same with 217 here. So to represent that number, I need 128, 64, 16, 8, and 1. And those will be marked with 1 and the rest with 0. I just want to move over these pretty quick so we can move on with the topics. So let me write that here. So 128, 64, 16, 8, and 1. And the rest are marked with zeros. So this one would be equal to 200 and this one would be equal to 217. And we can actually verify that with a converter. You can see that I've already done that here. So let's see if I got that right. 11011 11011 and then let's see 200. So 11001000. I think that was accurate. Okay, so now that we have these numbers, let's convert the full network addresses in binary. So let me make some more space here. Let me get rid of all this. So 10.42.200.0 would be 0001010 dot 00101010, and then what we just had on the screen, 11000100, and then finally 00080. There we go. And then for the last network address in that range, it would be like this. I don't want to repeat all the ones and zeros. You can see them on the screen here. And then what did we have for 217? So I believe it was like this. And then, all right, so this is equal to 10.42.200.0, and this one is equal to 42.217.0. Okay, now that we have the numbers in binary, let's compare them to find the bit boundary where the bits stop matching. And this will give us the subnet mask and the network address. So you can see that the bits match all the way to this point. These two bits are the first ones that are not matching. The sequence breaks at this line. So what we would do is we would mark all the matching bits with ones and the rest with zeros. So we would do this. Well, let me align that a little bit better. So we have 8 ones here, and then 8 more. Then 3 ones, and the rest are zeros. Like this. Oh, I think I've forgot 1 0 from here. Yeah. So this one in decimal would be 255.255.224.0. So now the network address is derived by performing a logical AND operation between the networks and the subnet mask. So that would give us, let me actually use this ruler here to make like a nice little line here. Whoops. Oh, turns out that I can't write straight. That doesn't matter. Let's do it this way. Okay, so here is the AND operation. So what we would get is 0 0 0 0 1 0 1 0, and then the rest of the string that I don't want to repeat, and then here. So this would be 1 1 0, and the rest of them would be zeros, because anything AND, if you perform a logical AND operation with a 0, it's gonna be a 0. All right, there we go. And these are all zeros. So what the result is 10.42.192.0. So this is our network address, and this is the subnet mask. So if we write that in another format, using the prefix length, we get 10.42.192.0/19. And why 19 is because the first 19 bits match. So that's how we would get the summary route for these networks. So instead of these broader ones that I showed you before, you would have 10.42. Actually, let me write it on top here. 10.42.192.0/19. Like that. All right, now let's do the same with our 5's routes. So let me get rid of all these wonderful binary numbers here. Actually, let me make this a little faster. Like this. All right. So let me represent these networks in binary. So I'm not going to repeat the process of how I got to the binary number. I'm just going to write it down here. So 1 1 0 0 0 0. That's 192. Then 168. And then we have 47 in binary. 1 1 1, and then these are all zeros. Like this. So this is 192.168.47.0. And then the other one, so this one would all be the same. And then this part is going to change. The third octet is different. So it should be like this. 0, 1. I hope that I've typed that right. So this is equal to 192.168.114.0. And again, we find the bit boundary, which is right here. So then, again, we mark all of these bits as ones. And this will give us the subnet mask 1, and then the rest of them are zeros. Like this. Oops. So this is equal to 255.255.128.0. Let me use this ruler again. So we perform the AND operation to get the network address. So that is going to be 11000000, and then the rest of it like this. And here, so we are getting all zeros. So this would be the network address. So 192.168.0.0. So I actually this one wasn't too far off. But notice the little difference here. This is actually 17 bits that are matching. So the summary route would be 192.168.0.0/17. Let me write that down here as well. There we go. So the result is that instead of advertising all these specific networks, the routers can advertise the summary routes instead. Or alternatively, R1 could configure a static route this way. Yeah, we're just viewing this situation from R1's perspective. But as I mentioned, there are other methods to get the same result, but I like binary because bits don't lie. So that's it for this video. Thank you for watching, and I'll see you in the next video.